what we did was we actually derived an expression for the specific heat of solids, and we showed that at low temperature it goes as T cube, and at high temperatures it saturates to T, right? And in doing so, we used the harmonic approximation, and that was the only approximation involved. In fact, besides that, we didn't use any other approximation. So we said that we have a harmonic crystal. So these are the atoms, let's say, and then let me just draw them as points. So these are the atoms, and then they are going around their mean position. Okay. So this is what they are doing, and they are doing so in coordination, which means that they're coupled to each other, right? You know that they are coupled via these spring-like forces. So you can think of a spring between them. So this is our model of the solid, right? And you can extend it further down. Let's do it. And the spring constant here is K, and the mass is M, and this lattice extends to infinity. So we said that these are coupled harmonic oscillators. Atoms are coupled harmonic oscillators. And then we solve this problem as we would solve the problem of coupled harmonic oscillators. And what did we get? So if we have, let's say, a total number of atoms is n, okay, and let's say you have one atom. This is, for simplicity, one atom per unit cell. So when I say unit cell, I mean primitive unit cell, per primitive. So unless I specify that we are dealing with a conventional unit cell, you should always assume that it's a primitive unit cell, per primitive unit cell. Okay, we wrote the equations of motion, we solved it, we did it for 1D. Now we are dealing with 3D. So what was the solution? So the solution is that you will have 3n normal modes, right? 3n normal modes, right? And we will have k, which is the wave vector. K will take n values in the primitive cell of the reciprocal lattice, Wigner's side cell of the reciprocal lattice, which is called the Brillouin zone. So k will take n values in the Brillouin zone, or k will have n values in the Brillouin zone, and each value of k corresponds to 3 values of omega. So for each k you have 3 omegas, and those 3 omegas are the 3 acoustic branches. Because we are dealing with a monoatomic lattice, there are no optical branches. So there are 3 acoustic branches, and of these 3 acoustic branches, one is longitudinal acoustic and the other 2 are transverse acoustic, right? So TA1, TA2 and LA. Sorry? 2n what? Normal modes? No, this, I mean, I've drawn it as a 2D, but it's a 3D crystal. So the third direction is not shown actually. So it should be like this, you know. So it's a 3D crystal. If it is a 2D crystal, then you're right. Then it's 2D. Okay. We are writing quantum theory of solids. So we need to quantize these normal modes, right? So what was the deal? The deal was that if you have these omegas, omega 1, 1, omega 1, 2, omega 1, 3. What is this notation? The notation is that for the first value of k, which is let's say k1, which could be 0, the first value of the first branch, second branch, third branch, like this. So in general, you write omega, ये last time भी हमने किया था, omega k s, where this k, you know, is quantized, right? And you know, if you are along, for instance, kx direction, in the kx direction, the delta kx would be what? How much? Exactly, 2 pi by ax, and ax times nx, where nx is the number of atoms along the x-axis, and so on and so forth. This we did. I'm just trying to remind you of things. So, okay, so you have these omegas, and then you said that each omega, you can quantize it. So this is called second quantization. So if you're doing what is it called, quantum field theory, then you would quantize the waves, at least the electromagnetic waves, to get photons. So here when you quantize it, and this is a very important result, then we say that each mode is a quantum harmonic oscillator. And the energy of this oscillator is given by E or U or whatever. Let's write U, and this is given by N plus 1/2, and let's put some indexing on N, so it is the for some specific value of K and for some specific value of S, H bar omega K S, right? And what is this here? We had derived an expression for this. This is the distribution function. So phonon distribution function, right? So this is your distribution function. So this is the story of a real solid, quantum theory of a real solid under harmonic approximation. That is the only approximation we have made. Distribution function. And to be more precise, Bose distribution function. To honor Professor Bose, it was his contribution. And this, this is applicable to all the bosonic particles. That means particles with integral spin or zero spin. Good. This is what happens in a real solid. So you can say that you have these modes. Let me call them omega 1, omega 2, omega 3, omega 4, and omega 3n. So you have these 3n modes. Now I have not put the index, this S index I have not put. I have taken this as that S index in this counting because I am writing 3n explicitly. Otherwise I will write up to n, but for each we will write 3. It is the same thing. All these are different, right? And in fact, you know that in 1D, you even know the functional form of omega. In 1D, the functional form we have derived under root 4k by m sine mod sine ka by 2, where k is the wave number and capital K is the spring constant that sits in front, right? So this is the reality. And now, if you draw a harmonic oscillator corresponding to this, so that will look like this. And if omega 1 is very, very close to the zone center, then these energy spacings will be very, very close. Wouldn't they be? They are all equally spaced because the spacing is given by this, but they are very closely spaced. It is almost a quasi-continuum, right? When you will come somewhere here, the form of parabola will remain the same because that is determined by the spring constant. But now the spacings are a little wider. And when you come towards the zone boundaries, then this spacing will become even wider. And so. So that is the reality that is what is happening in the real solid. And what you do is you say that, okay, let's say at any temperature T, you say at any temperature T, right? Now you compare this T to the energy spacing, T compared to the energy spacing, okay? So if kBT is very large compared to the energy spacing of even this oscillator, then you would say that you have excited all the modes, isn't it? You have excited all the modes. And remember, when this oscillator is here, for instance, what is this level? This is 0, this is 1, this is 2. So what you would say is that you have a phonon. You have two phonons because you are at 2. Suppose you are at 2. You will say you have two phonons of energy h bar omega 4. When this is at 10, you will say you have 10 phonons of energy h bar omega 4. Okay? Now you can imagine if this guy is at 2 and you say you have two phonons corresponding to omega 4, then the same energy, if you take here, and because the energy spacing is very close, what would you say? You will say you have 25 phonons of energy omega 1. See, at the same temperature, different modes have different occupancies, isn't it? That is the whole essence of it. So even at very, very low temperatures, so when you go to very low temperatures, so that means the temperature is so small that you cannot even populate this first level of the modes that are near the zone boundaries. Why? Because the energy spacing is too large, the temperature available is too small. Okay? Then you would be exciting only the modes close to the center. But you will continue to excite some modes or the other, because the energy spacing will go on decreasing. You have all sorts of energy spacings available to you. So no matter howsoever low the temperature is, you will be able to excite some phonons, right? Now today we will deal with a model that was given in 1907 by none other than Einstein. So what is Einstein's model? He said, in the solid that I have, there are n atoms. Each atom has 3 degrees of freedom. It can vibrate along the x-axis, along the y-axis and along the z-axis. So he said that let's model it as a 3-dimensional harmonic oscillator, right? So therefore, each atom now is a 3-dimensional harmonic oscillator, 3D harmonic oscillator, right? So its energy eigenvalues are given by nx plus ny plus nz plus half h bar omega. Huh? 3 by 2 h bar omega e. That's all he said. So therefore, how many harmonic oscillators you have to deal with? You have to deal with n three-dimensional harmonic oscillators, or you may say 3n one-dimensional harmonic oscillators. It's the same thing. And these are his harmonic oscillators. A solid in terms of oscillations of, coupled oscillations. He decoupled it. He said the atoms are decoupled from each other. So there is no reason why this atom should vibrate at a different frequency compared to this atom. Right? That is his thinking at 1907. That is how he perceived a solid to be. So we call it an Einstein solid, where each atom is oscillating with a frequency omega e, and it is decoupled from its neighbor. Whereas the reality is this. The reality is what we have been doing over last 4 lectures. This is the reality, and this is what Einstein's perception of a solid is. Now, if this is the perception and if this is the model, if we take, I don't want to do any maths. You tell me where will this land up? You tell me what should happen to the specific heat of such a solid at very high temperatures, very high temperatures. At very high temperatures, there is no distinction, there is no distinction in the sense, here also you will populate all the modes, here also you will populate all the modes. So both the models will converge. Einstein model will converge with the reality at high temperatures for sure. This is going to happen. We will prove it mathematically also. Now let's talk about low temperatures. What's going to happen at low temperatures? Look here. Look here. This is reality. No matter howsoever low the temperature is, you still have oscillators you still have phonons. If we talk in terms of phonons, you still have phonons, right? If you may not have phonons in this mode, for this oscillator, but you may have phonons for this oscillator or this oscillator. It all depends on the temperature, right? On the other hand, what is going to happen here? Once you go to very low once you go to temperatures that are smaller than when kBT is smaller than h bar omega e, that is the energy spacing, right? All the oscillators are going to come down to their ground state. The specific heat is going to fall down exponentially. There will be exponential drop of the specific heat. And that was the failure of Einstein's model. That the specific heat at very low temperatures in Einstein's model goes down, goes to 0 exponentially fast, whereas in reality it goes as T cube. Okay? So let's try to see that. Now things are going to be much easier to calculate. Why? Because energies are same. So what will be the energy of my solid? Vibrational energy of the solid. Now we are dealing with Einstein's model. So in Einstein's model, what should be the energy of the solid? Energy of each harmonic oscillator, okay, and then you multiply it with 3n, or you add it up, whatever. So you say oscillator number I, Ni, plus 1/2 h bar omega e, okay, and now there is no index on it because for all the oscillators omega is the same because the oscillators are all independent, they are decoupled. That's the difference. Reality is coupled oscillators, Einstein's model is decoupled oscillators. Sum it over all i's, where I go from 1 to 3n, right? This 3 is coming because we are dealing with 3-dimensional solids, 3 degrees of freedom, 3 harmonic oscillators. I have written it as 1. Bas, now we are done. Now we have to do some maths to get. Now let me see if I have my notes. I do have. So you know what is n? N is the same distribution function. That was the ingenuity of Einstein. He realized that this is a quantum problem. Right? He treated the solid as a quantum problem. That's why he said this n should be given by the same distribution. And he was inspired by actually Planck's theory of black body radiations. So Ni is 1 over exponential beta h bar omega I, and then what is it, plus 1 or minus 1? Minus 1. I keep getting confused. So what we have to do now is put this here. We will get the energy, the vibrational energy, and then what should be the specific heat? Del U del T. I mean, actually the specific heat is del Q del T, but you assume that all the heat is going into exciting the vibrations. Nowhere else, no heat is lost. So you can do that. So I am not going to do the maths. So I will just write the expression. C is del U del T, and this is equal to summation I 1 to 3n. Now you put this guy here, and it has the temperature dependence. So you have to differentiate it. Okay? So differentiating is not difficult. Right? In fact, this will come out because this is temperature independent. This will get cancelled, 1/2 will get cancelled, 0 point energy. So you see, one day you are asking me, what's the role of 0 point fluctuations? The 0 point fluctuations do not contribute to the specific heat, right? The moment you take the derivative, this disappears. So the only term which is temperature dependent is Ni, where the temperature dependence is coming is Ni. And even in Ni, your these are not omega i's, these are omega e's. So that is the essential difference, right? So even these are constants. So the only temperature dependence is sitting over here. Whereas if you are dealing with the real solid, then even this is temperature dependent, right? That is the difference. Omega is also temperature dependent. So I will let you do it. So can you do this and tell me what is the answer? So let's settle first a few things. Do I need to continue with the summation? I am summing over what? Summing over what? Ni's, right? In Ni there is no I, so that means this Bose factor is same for all the terms, isn't it? So summing over this I can simply write 3n, isn't it? I mean, because I am doing the same sum 3n times, isn't it so? So at least I don't have to write this again and again. So for summation I wrote 3n. Okay. H bar omega E is also temperature independent. And then what remained is just del T of this factor, 1 by exponential beta h bar omega E minus 1. Now if you differentiate it carefully, which I am sure you would, then what you are going to get is 3n h bar square omega E square divided by Kb, Boltzmann constant, and then you will have derivative of this will give you exponential beta h bar omega e divided by exponential beta h bar omega e. It's like 1 by x, so it will be minus 1 by x square. So you have to have the square of this. And then you have to differentiate this fellow. So this is 1 by kt. So its differential will be 1 by kt square with a minus sign, and that minus and this minus that you will get from differentiating 1 by x will get cancelled out. So you will get 1 by t square. And that kb got cancelled. So that is taken care of. So this is what you will get for C. That is it. Done. This is the specific heat of Einstein solid as a function of temperature. Now the homework problem is to use a program of your choice to plot this function as a function of T. So it has a temperature dependence, which you can see sitting there. But in the good old days, we used to plot functions not by using a program, but by just looking at the behavior of the function at the extreme limits, finding its maximas and minimas and so on and so forth, right? You may have done that. So let's try to look at the behavior of this expression, or I should say the specific heat of Einstein solid. Now this is Einstein solid, the specific heat of Einstein solid at very low temperatures and very high temperatures. You know the answer, at least for the very high temperature, the answer should come out to be 3R, because then it's not very different from this, right? Because the temperature is so high that all the modes are excited, doesn't really matter. So let's try to see. So first let's try to see what will happen if the temperature is very high. So kBT is the energy accessible to the oscillators, is much greater than h bar omega e. So all these oscillators have large n values, right? Now what should happen to this expression? Who will tell me? So I can write this as 1 by beta. So this will be 1 much greater than beta h bar omega e, or you can say beta h bar omega e is much smaller than 1, right? Now with this expression, so now let's call this as x. So when x is much smaller than 1, then what should happen to this expression, which is some constant times e to the power x divided by e to the power x minus 1 whole square. Huh? Very good. Then further.
For high temperature, then it will close to 1.
It will be close to 1 then.
And it will be 3R.
Right. So the temperature dependence will cancel out. Do it.
To expand that cancel factor like
Do it. Yes, do it. X is much smaller than 1. Then what should happen? 2e to the power x minus 1. Tell me what is the answer. Sorry? Fantastic. How did you get 3R? Because the answer is not 3R. How did you get 3R?
High temperature limit, it will be 3R.
Are you also getting 3R? What are you getting? Be careful, huh? Don't give an answer which you already know is the answer. Work it out and then give me the answer. Because the answer is not 3R, at least in the current form, unless you do something to make it 3R. Hmm? 3 NKB is the correct answer.
Taken n equal to
Ha, now when you take n equal to NA, then it will become 3R joule per mole. So right now the expression that we have is not for the specific heat, but for the heat capacity, because we haven't fixed the number of atoms. The moment you fix them to 1 mole, then you get 3R. Fantastic. So when x is much smaller than 1, C will tend to 3 N Kb, and if you write C molar, which is the molar specific heat, so C mole, then that will be 3 Na Kb, and that will be 3R, and that will be R is 8.314, so that is 24 point something 34 whatever, 24.4 or 5, and units joule per mole per Kelvin. So even the Einstein solid also has the same specific heat at high temperatures. So can you now quickly tell me what you did, because I have to convey this to all the students. So what did you do? Because you're good with maths.
when beta h plus omega is much more less than 1,
Huh?
then the numerator factor will be 1.
Huh. So what you did is you said 1, so you said e to the power x when x is much smaller than 1, so you expanded it and you wrote it as 1 plus x square by 2 factorial plus so on and so forth. So you can ignore to throw everything from the numerator, just keep 1. So it's close to 1. And from the denominator, you will be left with just x, because in the denominator, you can take 1 plus x, right? Now you may say, why are we not taking 1 plus x here also? Well, take it. If you take 1 plus x here also, meaning if you throw away all the terms beyond x square, then you will get 1 plus x here, and you will get just x here, right? So you will get 1 by x plus 1, and 1 by x will again tend to 0, because x is very small. X is very small. Sorry, x is, sorry, what did I say? Hmm?
X will be less than 1, that's all.
X is very small. X is less than 1.
Can we cancel the other term? That's all.
Huh. So that we will do in the other extreme. So the other extreme is when KBT is, oh, I shouldn't have erased this, because the fun part is now. This is the trivial part. So let's do the fun part, which is when KBT is much smaller than h bar omega e. Right? Or you can say that in this case, beta h bar omega e will be what? So will be much greater than 1 or you can say if you're calling it as x, then x is much greater than 1, right? So in this case, what can you do? You can write e to the power x minus 1, because x is a very large quantity. So we are dealing with this case now. So let me erase it. So we are dealing with this case. Since x is a very large quantity, therefore e to the power x will be a very large number, and therefore e to the power x minus 1 is not very different from e to the power x, right? So if you invoke that, then here you will have e to the power x divided by e to the power 2x. So it will be e to the power x, right? And then you can readjust the terms. So basically what you are going to get in this case is something like this: c is equal to 3 kb n, and then h bar square omega sub e square divided by kb square. So I'm purposely writing it like this, and then you have exponential minus beta h bar omega e divided by t square, right? Sorry. And if you want to write little c, that is c molar, then this will become c divided by Na, right? So for 1 mole, so that will, here you will replace n by Na, so this will become 3R. Okay, so this is what you get. So how does it go to 0? It goes to 0 as e to the power minus x, right? So if you have to plot this, so this is your e to the power minus x, and this is your t square sitting here. Okay.
It will go to 0 as x square e to the power minus x.
Okay, so if you are working in terms of x, then your x is what?
Beta h omega e.
Beta h omega e. So,
You can take kb square t square as beta square.
huh?
It will become beta square h square omega e square.
Yeah. So this is 1 by kt.
Yeah.
So this is kb. So this is t. This is x, right? So now if you plug it in here, so you will get something like exponential minus x and x square, right? And if you plot this function, how does it look like? How will x square e to the power minus x look like?
The case at the infinity and at the origin it will be like parabola. So it is, yeah.
The low temperature is a critical force with x.
So you can plot this. So this is how it goes. So if you plot the specific heat C molar for the Einstein's model, it will look like this. Temperature C molar. So it goes to 3R limit at high temperatures. So the Einstein specific heat of Einstein solid is going to come down which is what happens in real solids. But here it goes down like this. Okay. All right. So the problem with this model is that at high temperatures it works pretty fine, but at low temperatures it doesn't reproduce the experimental data. Experimentally, the specific heat in this region goes as T cube, which we have shown for our actual solid. We derived the relation. But for Einstein solid, the specific heat here goes as given over there. So it doesn't go as T cube. Okay. So what if you look in terms of dispersion, if you look in terms of omega versus k, though Einstein did not look at it like this, but once again I'm saying that if we do it that way, so here is the zone boundary. So the actual dispersion looks like this, but the Einstein's model, for the Einstein's model, Einstein took some frequency omega e, which you can adjust to get the correct values. So in his case, the frequencies are independent of k, right? So in Einstein's model, this is the dispersion, omega e for any value of k, which is what I had written here, right? So omega e for one first mode, second mode, for everything is just, so it's a flat dispersion. Now, why did I say Einstein model is still useful? It is still useful because when you are modeling the specific heat of real solids, polyatomic solids, so you have both acoustic as well as optical branches. So you can model the optical branches using the Einstein's model, because the optical branches, they go like this, right? They go like this, right? So in the first approximation, you can take the optical mode as the Einstein's.
Slope near the boundary points are very close to zero. So that's why.
This slope is 0. This slope is also 0, and there is some curvature in between. But to a first approximation, you can just say, so you can model your real solid when you're modeling the specific heat. You can model the optical branches using the Einstein term, and you will model the acoustic branches using the Debye term that we will discuss in the next class. So I will stop here. I didn't do this part very nicely, but I'm not very sad about it, because you guys should do it yourself. Go home. This is the expression. Analyze it in the low temperature limit, high temperature limit. Plot it for low temperatures, high temperatures, over the whole temperature range and so on. Play with it. But you see, getting the expression for specific heat or for heat capacity is straightforward. It's a trivial thing, right? So the maths is not difficult. This was one paper. It's a one publication, right? Einstein's publication. He published a paper with this calculation. Now, calculation per se is very simple, but the idea that that the solid should be seen like this, and at that time, was remarkable. You can stop.